Hello and welcome back to my channel. Okay, so continuing on with the ultrasonic sound listener, I've updated the whiteboard diagram to show the fact that the microphone and preamplifier are contained in one unit. I've included the high-pass filter in the functional block diagram, because we identified in the previous video that there are things happening as far as spectral inversion goes that could be undesirable, and it could be a good idea to filter the frequencies that are in the audible spectrum before passing them on into the mixer. So the idea for this high pass filter is that ultimately, nice to have, is that it should track the frequency of the local oscillator as well. So because our whole goal is to maintain the local oscillator frequency less than the lowest frequency in the output spectrum. So in this case, the low frequency here would roughly correspond to the corner knee frequency of the high pass filter. Now, as we'll see later, it's impossible to design a high pass filter that has a purely vertical response and then a horizontal response. They all have a slope at the break frequency. And okay, so continuing on, the bat had to go because I had to make room for the new diagram here, and the rest of the block diagram is pretty much the same as it was before. So I've added the high pass filter and perhaps a bypass switch where we can switch quickly from direct output from the microphone to output from the high pass filter, and to see if there is really a difference in filtering out the audible frequencies before passing them to the mixer modulator. Okay, so that about wraps up the block diagram, and now we'll move on and start looking at the actual hardware circuit components. Okay, in this video segment, we'll examine in detail the first signal processing block that was shown on the whiteboard diagram right after the microphone preamplifier, and that is the high pass filter. So you can go to a website by Okinawa Electric Design, here it is, and you will find a filter, active filter, high pass or low pass design tool. It's an online calculator that allows you to calculate the capacitor and resistor values for a filter with a given cutoff frequency. So what you'll see on the website is like a textbook example, like the one shown here, an op-amp with a resistor and capacitor network in its feedback network. Positive, in this case it's in the positive feedback network, and the negative feedback is unity gain, corresponds to unity gain. So starting off with the textbook example, I developed my own version of it to accommodate the biasing, the DC biasing that I need to incorporate to make it work for a single power supply. And basically the only change I've made is, in place of a single resistor for R3, I have two in parallel, where I've connected one to V+, the positive supply rail, which is about there. So the action of these two parallel resistors is to act as a voltage divider, and have the 50% of the positive supply appear at pin 3. So for DC, these capacitors basically act as open circuits, and it's unity gain for DC, so whatever appears at the voltage at the junction of these two resistors, half of 12 volts being 6 volts, will also appear at pin 6 volts. So the reason I want 6 volts, I want the output to float at 50% of the positive supply rail, because when I apply an input signal, I want the output to be able to swing basically almost 6 volts upwards and almost 6 volts downwards, for a total of 12. In reality, I probably won't get that. You'll probably get a maximum of 12 volts, 10 volts, sorry, of positive swing, and maybe down to 2 volts on the lower swing. So that will sort of maximize the dynamic range I have with a 12 volt power supply, about plus 5, maybe minus 5 voltage swing on input signals. So from the Okinawa Electric design website, if I want a Butterworth filter with a maximally flat response in the passband gain, I can compute these resistor and capacitor values. So 1.5 nanofarads for all the capacitors, R1 3.9 k ohms, R2 1.5 k ohms, which in my case I've sort of daisy chained 2 resistors of 1.2 k ohms and 220 ohms, because I ran out of 1.5 k ohms. And R3 that corresponds to this diagram, I've created out of paralleling 2 55 k ohm resistors. So if connecting either resistor either to ground or to V plus from a DC or AC analysis point of view, it amounts to the same thing. It is as if both are in parallel connected to a constant voltage, either ground or V plus. They act in parallel. Okay, so let's go on and look at the filter response curve and how to characterize the operation of these filters. Okay, that's the next page. So what we do is we plot the output voltage versus input voltage of the filter, their absolute value, on something called the Bode plot. So you can take the a Bode plot is basically a plot where the horizontal axis is on a log cycle scale, and you can also choose the vertical axis to be log cycle, base 10 log, and you'll get a curve that looks like two straight lines. A horizontal curve that corresponds to the passband of the filter, and a sloping curve at the filter's break frequency or corner frequency that slopes downwards at 18 for a third order filter, 18 decibels per octave. Well, what is a decibel? Well, a decibel is a unit of sound measurement. It's a relative measure. In this case, what the relative quantities being the ratio of the output voltage to the input voltage. If I take the absolute value of that, take the base 10 log and multiply by 20, the result is the change in decibels of output versus input. So for 0 decibels, that would mean basically the output is equal to the input, and minus 3 dB is a barely noticeable, to the human ear probably just noticeable, drop in intensity. So the corresponding ratio of output to input is about 0.707. If you take the base 10 log of that and multiply by 20, you'll get minus 3. And if I drop the frequency, in this case it's a high pass filter, so as I drop the frequency, its output diminishes by roughly about 18 decibels. So if I go from where I'm designing the 20 kilohertz cutoff point, if I drop the frequency another half that to 10 kilohertz, I should roughly drop by 18 decibels, down to minus 21. And going from 10 kilohertz to 5 kilohertz, I'll get another 18 dB drop, which of course should correspond to the output being 39 decibels below the output. Just fairly significant. Although you could probably still hear that. That's a characteristic of human hearing, is that we do not respond, our ears and brains do not respond to linear ratios of sound changes, but rather logarithmic changes. So now there's this, I've been talking about octaves and doubling of and halving of frequencies, so what do they have to do with each other? Well, traditionally in music theory, an octave is doubling or halving of pitch, and there's, for every halving or doubling of pitch, there's 8 notes in the musical scale. So hence the use of the octave notation for characterizing the attenuation rate of filters. Now, it is possible to have a sharper slope to this curve or this knee by using more filter sections. So what I can do is I can cascade 2 filters that are 3rd order each, one after another, and I will obtain a 36 dB per octave roll-off filter, high-pass filter. Mind you, the drop frequencies, the corner frequencies at 20 kilohertz for each one must correspond to minus 1.5 dB rather than each one at minus 3.3 dB, because minus 1.5, the net result will be minus 3 dB at 20 kilohertz. And that's how these filters are characterized, is that their corner frequency being defined is when their output drops 3 decibels below their passband. So if plotted on a horizontal log scale versus a vertical log scale, this is what the filter characteristic curve should look like, output versus input. Mind you, if you're plotting this function 20 log 10 V out over V in, the vertical scale should be linear, because this already takes into account the logarithm nature of it. So yeah, you can plot V out over V in on a log scale, or 20 log 10 V out over V in on a linear scale, and to obtain this linear sloping curve versus a horizontal flat curve. Okay, so that about summarizes the behavior in graphical terms of this circuit. So now we'll actually have a look at it on the breadboard and on the oscilloscope. See what we actually have. Okay, this is the high-pass filter next to the Electret microphone. The output of the microphone right now is not connected to the filter, but this is the output wire. The filter is fed at the moment by a lead from the signal generator right there. This is the first input capacitor, and the input is also monitored right here by the oscilloscope probe. The output of the filter, pin 6 of the TL071, right about there, is also monitored by the oscilloscope probe. So sort of start from input to output. Vn being applied to C1. This is C1 right there, first capacitor. This would be R1 resistor, the 3.9K. Capacitor C2, they're all the same. Capacitor C3. And these two resistors comprise the ones that are daisy chained 1.2K and the 220 ohm resistor, maybe not necessarily in that order, but here they are, going from the junction of C2 to C3 to pin 6 output of the op-amp. And the negative feedback loop is taken from pin 6 back to pin 2 by this jumper wire right here. So pin 4 of the op-amp is the ground wire. Pin 7 is the V plus, positive 12 volts, and this is this little capacitor here is the power supply bypassing capacitor. So R3A, R3B resistors are right here. So one is connected to ground and one is connected to V plus pin 7 to form the voltage divider. It serves dual purposes: to divide the voltage that applies to pin 3, and also as the computed R3 value of 27k ohm value in parallel as per the filter design tool. So that's about the extent of the breadboarding of the filter. Let's have a look and see if the output actually does sit at 6 volts. See, as we require it to be. So I'll hook up a voltmeter as soon as I turn it on. Okay, so let's just touch the probe of the voltmeter to pin 6, which is also the oscilloscope probe. Oh, it's on AC. Okay, there we go, DC. And 5.98. 5.98, that's pretty close to 6. So, yes, it works. At least that part of it does. Okay, so I have the oscilloscope on display in the video camera now. So what I'm doing is I'm feeding a 80 kilohertz frequency into the high-pass filter at 4 volts peak to peak, and which is the yellow trace here, and monitoring the output on the channel 2 of the oscilloscope, which is the purple pink trace here. So right now the signal is way up above the cutoff frequency of the filter. It's in the in the passband gain, passband of the filter, and the output and input should almost be identical, but they're not quite. So I get 4 volts of input, I get 3.8 volts of output peak to peak. And I'm suspecting that the capacitors that I'm using, the C1, C2, and C3 in the that were given by the filter design tool on the website, here they are in fact have some effective series resistance that we'll check in a little while. See, these are ceramic caps, and they're not the best for signal processing applications. Should be using metal film capacitors, which I'll probably end up changing as soon as I get a hold of them, but at the moment the ceramics is what I had. So I'm going to lower the frequency now. I'm going to go down to 40 kilohertz and see what the change in the output is. Okay, 40 kilohertz, 3.76 volts, not much, shouldn't be. So now, incidentally, for a 3 dB drop from the input of 4 volts, if I quickly compute that on my calculator, 0.707 times 4, should correspond to about 2.8 volts at the output. So let's go down to 20 kilohertz, and there it is. Yes, it's right there, 2.8 volts. So the corner frequency looks like it should be pretty good. And now we'll drop it down another octave, go down to 10 kilohertz. And let's increase the vertical scale so we can get a better reading. Okay, so we've got about 520 millivolts at the output versus input of 4 volts. 520 millivolts at 10 kilohertz. And now if we go down to 5 kilohertz, I can barely see it now. Now let's just increase, let's slow down the scope and also increase the vertical scale a bit. Okay, so peak to peak measurement is about, it says 110 millivolts, but as you can see, some of that could be a little bit of jitter and noise riding on the wave. So I would call it at 75 millivolts instead of the 100. We'll do a few computations to see how that corresponds to a 18 dB per octave drop. Okay, I've done some calculations, gain change calculations from the oscilloscope measurements that we had. So at here's the first one. At 20 kilohertz, I have an output of 2.64 volts versus an input of 4 volts. I set the oscilloscope to a little bit of a higher sensitivity setting. I increased the vertical scale, and I got that as opposed to the 2.8 volts. So the computation yields minus 3.6 dB drop, which is fairly close to 3, minus 3 dB. And if I go an octave below that, half the frequency, I get 0.52 volts versus the previous 2.64 volts. So we're always looking at the change from the previous. So 20 log times that ratio is about minus 14.1 dB. Not quite 18 yet, but you know, these could be also measurement errors. And second other halving of frequency down to 5 kilohertz, 75 millivolts versus 0.52 volts, I get minus 16.8 dB. I'm getting close to minus 18. An 18 drop from 10 kilohertz down to 5. So it looks like the filter more or less, yeah, it is working more or less as intended. Now, the passband attenuation, I get a little bit of a passband attenuation. So at 80 kilohertz, which is well within the passband of the filter, the output as peak-to-peak output 3.72 volts versus an input of 4 volts gives me an attenuation of minus 0.63 dB. That's at 80. So this is at 80 kilohertz. And now if we go back to here, to the corner frequency at 20 kilohertz, this minus 3.6 dB already contains this minus 0.6 dB. So in fact, if we were to take this away from that, because our passband gain is not 0, it is minus 0.6, this is actually minus 3 dB, which is spot on for its cutoff frequency, its corner frequency. Now, why are we getting minus 0.63 dB instead of almost 0? Well, I have a feeling that these capacitors that I'm using have a effective series resistance, which we can check with an LCR meter. So I have one in the LCR meter right here. I'll turn it on, but you can't see where the capacitor. I'll zoom it out a bit. But anyways, it's in there, right there. Wait for it to it's set on ohms. Okay, I have to change the range. Okay, there we go. So what do we see here? 1431 picofarads, which is fairly close to 1500 picofarad or 1.5 nanofarad, with an effective series resistance of 880 ohms. Well, 880 ohms. We need to reanalyze this circuit at the passband gain if we were to replace these capacitors at passband with 880 900 ohm resistors and see what we get as far as an output to input ratio, which I might do in the next video, or yeah, if I have time. But I suspect that's what's causing the output to drop a little bit, is effective series resistance. Okay, that might put a wrap on this part 3, and in part 4 we'll start examining the local oscillator and modulator.